All right, let's dive into one of the most critical parts of any high-performance application, caching. We're going to break down how to design systems that are truly enterprise-grade, systems that can handle millions of users without even breaking a sweat. Let's get right into it.
So, here's the game plan. We'll kick things off with the fundamental why, the real problem that caching is built to solve. Then we'll start building our solution layer by layer. We'll look at the different read and write strategies, figure out how to be smart about what data we keep, and finally, and this is a big one, we'll learn how to stop our cache from accidentally causing a total system meltdown.
Okay, so first things first, why do we even need to bother with caching? Well, it all boils down to this huge, unavoidable gap in speed. And trust me, this gap is the silent killer that slows down pretty much every application as it starts to grow.
And this is where it gets kind of crazy. Look at the numbers. A CPU does its thing in nanoseconds, but fetching data from a database? That takes milliseconds. We are talking about orders and orders of magnitude here. It's thousands, sometimes millions of times slower. Now imagine what happens as your traffic starts to spike. Every single one of those millisecond delays starts to add up, just hammering your database and grinding your entire application to a halt.
And this is where caching swoops in to save the day. It's the bridge across that massive speed gap. So how does it work? It's all about something called the principle of locality. It sounds fancy, but it's actually a really simple idea. Most apps tend to ask for the same small set of data over and over and over again. Caching just keeps that hot data in super fast memory right next to the CPU where it's needed.
So, and this is crucial, caching isn't just some nice-to-have performance tweak, it is an absolute strategic necessity. First, it takes advantage of that locality we just talked about. Second, it's a game changer for scalability. I mean, in most big systems, you're looking at reads outnumbering writes by at least 10 to 1. Caching just soaks up all those reads so you don't have to keep buying more expensive database servers. And third, it gives you resilience. It's your buffer, your shock absorber for those sudden traffic spikes that would otherwise just knock your whole system over.
Okay, so we're all sold on caching, but here's the thing. At enterprise scale, just one cache isn't going to cut it. The real solution is to think in layers. You've got to build up your defenses, with each layer doing a very specific job.
Just think of it like a series of checkpoints, each one getting faster and closer to your application's core. Way out on the edge, you've got your CDN, things like Cloudflare. It keeps static stuff, images, CSS, physically close to your users all over the world. Then you come one level in, right on the application server itself, and you have the local cache. Something like Caffeine gives you nanosecond-level access to the data that specific server needs most often. And finally, you have the distributed cache, like Redis, which creates a shared memory pool that all your servers can tap into, keeping everyone's data consistent.
All right, so you've got your layers all planned out. The next huge decision is how your application is actually going to talk to them. And this is all a big balancing act between pure speed and making sure your data is always correct.
When it comes to reading data, you've basically got two main choices. The most common one is called cache aside or lazy loading. In this pattern, your application is the boss. It checks the cache first. If the data isn't there, that's a cache miss. It's the app's job to go get it from the database and then pop it into the cache for next time. The other way is read-through. Here, the cache itself does the heavy lifting. Your app just asks the cache for data, and if it's a miss, the cache provider automatically fetches it from the database for you. It really cleans up your code.
Now, writing data, that's where it gets even more interesting. With write-through, you write to the cache and the database at the exact same time. It gives you really strong consistency, but it's a bit slower. For maximum performance, there's write back. You write only to the super fast cache first, and then the data gets synced to the database later. It's incredibly fast, but you do risk losing data if the cache crashes before the sync happens. And finally, there's write around. This is where you just bypass the cache completely when you write, talking directly to the database. This is perfect for avoiding cache pollution from data that's written once and then rarely ever read again.
So, here's the problem we all face. Your cache isn't infinite. It has a limited amount of memory. So when it gets full, you have to make a hard choice. What data do you kick out to make room for the new stuff? That's where eviction policies come into play.
An eviction policy is really just a set of rules for making that decision. You can think of it like a bouncer at a really popular nightclub. When the club is at capacity, the bouncer has to decide who gets to stay and who has to leave to let new people in. A really good policy makes sure the most important VIP data always gets to stay inside.
Now, the classic bouncer strategy is LRU, or least recently used.
It's simple. It just kicks out whatever item hasn't been touched in the longest time. But it has this massive weakness. A single big database scan can come along and fill your cache with junk, kicking out all your valuable hot items. But a modern policy like WTinyLFU, which is used by Caffeine, is way smarter. It uses this clever trick called a popularity sketch that acts like a filter at the door. It only lets new items in if they prove they're likely to be more popular than what's already inside. It is so much better at preventing that kind of cache pollution.
So you've done it. You've designed this beautiful, multi-layered caching system. But you have to be careful, because if you don't implement it correctly, that system, the thing that gives you all that amazing performance, can become your single biggest point of failure, your Achilles heel.
This is the question every single system architect needs to be asking. Because when your application is scaled to depend on a cache handling 99% of its reads, the second that cache stops working, your database is about to have a very, very bad day.
Okay, catastrophe number 1, cache penetration. This happens when a bunch of requests come in for data that just doesn't exist. Not in the cache, not in the database, nowhere. Every single one of these ghost requests flies right past the cache and slams into the database. This is a huge deal because it can actually be exploited by attackers to launch a denial of service attack.
So, how do you stop it? You've got two great weapons. First, you can cache the null result. Just store a marker saying this doesn't exist for a short time, maybe 5 minutes, and that will absorb all the repeat requests. Or, even better, you can use a Bloom filter. It's this incredibly efficient data structure that's like a bouncer for your whole system. It can tell you almost instantly if a key doesn't exist, so you can reject the request before it even gets a chance to touch anything important.
Next up is the cache stampede. You might have also heard this called the thundering herd problem. Just imagine you have one single, incredibly popular piece of data, a hotkey, and then it expires. All of a sudden, thousands of requests all see a cache miss at the exact same microsecond, and they all stampede the database, trying to regenerate the exact same piece of data.
The only way to manage a herd like that is with control. You can use something called a distributed lock. This basically ensures that only one request gets the token to go to the database, while everyone else patiently waits their turn. Or you can get ahead of the problem with a refresh ahead strategy. A background process just updates that hotkey before it even has a chance to expire in the first place.
And finally, we have the big one, the cache avalanche. This is what happens when a huge chunk of your cache keys all expire at the same time. Suddenly, that protective wall you built is just gone. A tidal wave of requests floods a database that was never, ever designed to handle that kind of load, and that can lead to a cascading, system-wide outage.
To prevent an avalanche, you have to stop everything from happening at once. And the simplest trick is something called expiration jitter. Instead of having every key expire in exactly 60 minutes, you add a little bit of randomness. One expires in 59 minutes, another in 61. It's a tiny change, but it staggers the load beautifully. And from an architectural standpoint, you have to treat your cache as the critical system it is. That means building a high availability cluster so that it's resilient and it can never just disappear on you.
So let's bring this all home. Caching is your #1 weapon for closing that massive latency gap. But it's not enough to just have a cache. You need a layered architecture. You have to make a conscious choice about your read and write strategies based on your needs. You should use smart, modern eviction policies like WTinyLFU. And most importantly, you have to design defensively from day one to prevent those catastrophes, the stampedes and avalanches that can bring your entire system to its knees.
Look, the question isn't if your cache is going to be tested under fire, it's when. So you have to ask yourself, is your cache, your system's first line of defense, truly prepared for the battle to come?